Hello everyone, we are on chapter 4 about general vector spaces. Today we are going to discuss section 4.5 on coordinates and basis. This is a particularly interesting section because it really challenges our notion of reality. But just taking a look at where we've been, we talked about real vector spaces, then subspaces, then spanning sets, then linear independence, and each of those we're building upon the previous one, and 4.5 is also going to do that. So the objective of this section is that we usually think of a line as being one-dimensional, a plane as two-dimensional, and the space around us as three-dimensional. It is the primary goal of this section and the next to make this intuitive notion of dimension precise. In this section, we will discuss coordinate systems in general vector spaces and lay the groundwork for a precise definition of dimension in the next section. So I really like the figures that they have in this section that really demonstrate what are we talking about when we're talking about coordinates and basis. So these figures show here what we normally think of as, coordinates in 2D space and in 3D space. Certainly, if you look at this one here on the left for 2D, here we have our x and y coordinates. We take it for granted that they are at a right angle from one another, they're perpendicular. The other thing that we take for granted is that the units along x are equal in magnitude as they are along the y-axis. So like a 1 here would have an equal magnitude as a 1 going along the y-axis. So there's like equal spacing, so to speak. And so then that also translates as well into 3D space. And so what's interesting is that up until now, we've been working in this standard rectangular coordinate system, okay? So when we have been discussing, vectors and vector space, and like we're given a point here, like this point P. So here you can see that it has coordinates here, A, B. When we look at that point P, there's a lot of ways that we could kind of describe P. We could say, okay, well, here is a point, it's got a point with its coordinates A, B, so that's one way. The other thing that we could do is that we could describe this as a vector here. We got its origin here. We could say that that is O, and that this terminal point here is P. So we could also represent this as a vector OP by its coordinates. So we could do it that way. The other thing that we could do is, if we're talking about this point P, we could also think of it as a vector that's a linear combination of the unit vectors. So don't forget we have our I and j unit vectors. So this would be like I here. Here we've got j. So in this instance, this vector here would be equal to ai plus our bj, whatever values that happen to be for a and b. So we've got a lot of different ways that we kind of can describe this system here. And certainly this would hold true here in the 3D. We'd have another unit vector of k for along the z-axis. But this is how we're used to really thinking about these things in these terms. But here is where everything changes. So what if we're not dealing with this standard coordinate system here? What if we're dealing with something different? What if now our x and our y-axis are not at right angles anymore? And same within the 3D space over here on the right. What if all of this now is skewed? So how would we go ahead and describe those coordinates? And how would we, somehow refer to the fact that there's been these changes in, our axis system? So how are we going to describe all this? So it's really kind of cool, this particular section. And hopefully many of you will maybe use it one day. So now we're going to have to come up with unit vectors for these altered coordinate systems that we might create. And, why would we want to do that? So if we're thinking about our normal rectangular system that we've always used, well, we're used to using it in geometry because we want to have, our axes in, equal units because we don't want to distort the shapes. We want to do it for ease of calculation. We might also be dealing with the same type of units. But what if you had systems where, you had things that had diverse units? Like maybe you wanted to measure time versus temperature, or maybe you had time versus, distance, or, whatever it was that you might want to do that might have diverse units. So changing these coordinate systems could be to your advantage. So we'll see how that works in the coming examples. So here's another picture here that kind of helps you visualize. So here, now certainly these are just examples, so this is not all of the ways in which you could alter your coordinate system. But here here's our normal coordinate system. We have equal spacing between all the different units. But here's one way that we could change it. So here we've left x the same, but now we've really stretched y. So now it almost looks like y might be, you know, twice the spacing of x. You know, we still have a perpendicular axis, but you can see that this particular system has changed. So that's one example. Or here you have equal axis spacing. So, you know, your spaces here on x and y are the same, but now all of a sudden you've skewed the axes. So now no longer is this perpendicular angle between the two of them, you know, 90-degree angle. Maybe it's something different now. So you could kind of take that idea where then now not only have you changed that angle between the axes, but now you've also maybe stretched one of the axes, so its spacing is now maybe twice that of the other. So there's a lot of different ways that you could potentially be manipulating this. So we get to our first definition. So we want to talk about the concept of basis vectors. So here in definition 1 says, if S is a set of vectors in a finite dimensional vector space V. So what does finite dimensional mean? That means that there is a finite set of vectors. So that's one thing to note. So when you see this word here, finite dimensional, that means there is a finite set of vectors in V. Then S is called a basis for V if A, S spans V, or B, S is linearly independent. So why in the world do we even care about this thing called a basis? Well, you want to think about it like this. You've seen all those alternative coordinate systems that I just showed you, but you want to think of the basis as describing that coordinate system. Like, how has it been altered? So we want to know, what is the basis for our coordinate system that we're going to be using? It doesn't have to be the normal rectangular one that we're always using. So this basis is going to describe, you know, the coordinate system of a finite dimensional vector space V. And so I just want to reiterate really quick then, if S is a set of vectors in a finite dimensional vector space V, then S is called a basis for V if S spans V and S is linearly independent. So you want to think of this set S as being a basis for V that's going to describe the coordinate system. And hopefully you notice that in parts A and B, we've already done those parts. So we already talked about spanning sets, and we already talked about linear independence. So now we're going to be using those concepts to just be able to describe our basis for our vector space, and then we'll have an understanding of how that coordinate system is going to work and what it's going to look like. So let's write this down. So set S is hopefully going to be a basis for describing a coordinate system. So let's look at example 1. Just realize that that has listed your standard unit vectors. And so for this, you're going to want to kind of take notes of a particular way of notating the standard unit vectors. Obviously, we've seen from previous sections and examples that they are linearly independent. So we have that. We also know that they span Rn. In this particular example here, this would be R3. Just realize that these do refer to the normal way of thinking about things. So they are going to form the standard basis for Rn. So that's something to note in problems. You're going to want to look at the language. So we describe these unit vectors that we're used to seeing, the standard unit vectors. They are going to form the standard basis for real space. But besides having the standard unit vectors be a standard basis for real space, in particular if we're looking specifically at, let's say, R3, but what if you wanted to have another basis for R3 that wasn't the standard basis? So how in the world would we end up finding that out? What if we wanted to have this alternative basis? So we wanted to have somehow some coordinate system that didn't look like our standard rectangular system that we're always used to seeing. What if we needed to have another basis? So if we look at example 3, it says show that the vectors v1, v2, and v3 form a basis for R3. Ooh. So we have to show two things, don't forget, from our definition. We've got to show that this set of vectors here, that they span R3. So A, we got to know, do they span R3? And then B, are they linearly independent from one another? Ooh. So interestingly, example 3 lets you know that you can kind of solve this kind of simultaneously by what you've learned before in the previous sections. So what do we want to do? We want it to be able to show that they are linear independent, to show that v1, v2, and v3 are linearly independent from one another. Well, what do we got to do? We got to set up that homogeneous system. So remember from the previous section, we've got to set that up. That means that C1, v1 plus C2, v2 plus C3, v3 equals 0. So there's our homogeneous equation there. And then if we wanted to also be able to determine if these vectors span R3, we need to be able to show that that for every vector b, that we could express it as a linear combination of those vectors. So here we would set this up to C1 v1 plus C2 v2 plus C3 v3 now equals an arbitrary vector b. So hopefully you kind of remember that from our spanning sets section. I want you to realize that these are two very separate concepts. I'm going to draw you a little picture that I hope will provide some clarity. So we have this set S of vectors, and here we have v1 and v2 and v3 in here. So this homogeneous system here is directly letting us know, okay, are these vectors v1 and v2, are they linearly independent from one another in this set S? So this is set S here. Keep in mind, set S is not a subspace, it's not a vector space, it's just a set S. And we talked about linear independence in section 4.4, and that's where we use the homogeneous system to determine, are these things linearly independent of one another? So they're not going to be a linear combination of each other. Then though, now we're over with this side, where we have it set equal to B, we want to know, suppose we have this real space R3. Well, we want to know, does this set S span R3? And we should be able to show that for every vector B that might be in R3, it will be a linear combination of our v1, v2, v3. And so we learned about all of this from our section 4.3 about spanning sets. I hope I have the right number of the sections. But anyway, the name of the section was spanning sets. So we're doing two different things here. But if we can do both of these things, that we can show that the vectors in S are linearly independent, and we can show that S spans R3, then we're going to be able to determine that, yes, S forms a basis for R3 in describing the coordinate system. So now our basis and our coordinate system are going to go hand in hand, and you'll see that as we go through some of these things. So let's go ahead and explore this example a little bit further. To determine if those vectors in example 3 form a basis for R3, we're going to be looking at both of these linear systems at the same time. So one's going to show the vectors are linearly independent. The other one's going to show that for every vector in R3 is going to be a linear combination of those vectors in S. So we can go ahead and express these as our linear systems here. So using the information about our vectors, so we got v1 again equals 1, 2, 1, and we've got V2 equals 2, 9, 0, and we have V3 equals 3, 3, 4. So we can do both of these systems at the same time. They're just going to equal something a little different. So we have 1C1 plus 2C2 plus 3C3 equals 0 on this side, and then we got the same thing here, 1C1 plus 2C2 plus 3C3, except now it's going to equal B and B1. Then we have 2C1 plus 9C2 plus 3C3 is going to equal to B0. And then we have 2C1 plus 9C2 plus 3C3 equals B2. And then we got one more equation to do. We've got 1C1 plus 0C2 plus 4C3 equals 0. And then here we have 1C1 plus 0C2 plus 4C3 equals B3. So now we need to go ahead and solve these systems. So to be able to show that these vectors are in fact linearly independent, we need to show that this system over here has only the trivial solution, and then over here that this particular solution is consistent for all values of B1, B2, and B3. But what's interesting to note and why they do this side by side is that even though this one's a homogeneous system and this one is set equal to our arbitrary vector B, you'll notice that both of them have the same coefficient matrix. And so you can go ahead and write that as such. So we've got 1, 2, 1, 2, 9, 0, and then 3, 3, 4. Now notice I said that this is the coefficient matrix, it's not the augmented matrix, because they both only have the coefficient matrix in common. And so here's where you're going to use your knowledge of matrices to kind of help you solve this. And so you'll notice that this coefficient matrix here is a 3 by 3 square matrix. And that's really going to come in handy for solving them both at the same time and really being able to determine if these vectors form a basis for R3. Because we'll look at this and you refer back to that theorem 2.3.8, and you're going to want to see if you can make some conclusions about A that's going to lead you to the answer. So if you have a square matrix like this, you would want to then obviously, to help you solve this, you'd want to say, okay, well, is it invertible? If so, then we can look at those other equivalence statements in 2.3.8. Another thing that we can look at is the determinant of this matrix A equal to 0 or not. If it's not equal to 0, well, that's going to be important for us to determine, because what do we know about that? Well, we know that if the determinant of A does not equal 0, then that does mean that, guess what? That AX equals 0 only has the trivial solution, which would lead us to be able to conclude that those vectors are indeed linearly independent. And you would also know by this theorem 2.3.8 that if the determinant of A does not equal 0, that you also know that AX equals B for every B, which would help satisfy this side. So really, it's going to come down to picking a few parts of this theorem 2.3.8 very strategically to help you prove both of these. And so yes, we would be able to say, yes, these vectors, so V1, V2, and V3 do span R3, and obviously they are linearly independent and form a basis for R3. Whew. Once again, here is your theorem 2.3.8 of your equivalent statements. You're going to want to become very familiar with them so that you can use them for these problems. I wanted to draw your attention next to our theorem 4.5.1, and this is the uniqueness of basis representation. And it says if S which is a set of vectors v1, v2, all the way through vn, is a basis for a vector space V, then every vector v in V can be expressed in the form v equals c1 v1 plus c2 v2 plus c3 v3, all the way on through cn vn in exactly one way. So what do we mean by this uniqueness of basis representation? Well, it means that you can't write, say, this point, like we'll just use the standard basis here for a second here, but if you have this point P that's described by its coordinates a, b, well, you can't write this point or this vector, if you want to describe this as a vector, you can't write it any other way and still expect to refer to this same point or vector. So you have that uniqueness property there. The next thing that I want to go over is definition 2. And this says if S equals v1, v2 through vn, so if S is a basis for a vector space V, and V equals c1, v1 plus c2, v2, all the way through cn times vn, is the expression for a vector in terms of the basis S. Then the scalars c1, c2 through cn are called the coordinates of V relative to the basis S. Okay, so those C scalars here, those are going to form your coordinates of V relative to the basis S. The vector c1, c2 through cn in Rn constructed from these coordinates is called the coordinate vector of V relative to S, and it's denoted by V sub S here. Now realize that this is written in comma delimited form. But you could obviously write this as well in matrix form, so don't forget that. All of these have abilities to be expressed different ways. So this in matrix form would look like this, all the way through Cn. And you're going to want to observe that V sub S is a vector in Rn, so that once an ordered basis S is given for a vector space V, this theorem, 4.5.1, which I showed you before, establishes a one-to-one correspondence between vectors in V and vectors in R. So keep that in mind as well. There is a one-to-one correspondence.